virus isn't alive, people. It's non-metabolizing. And look at it. I mean, either it's single-stranded or double-stranded RNA or DNA, and it just happens to have the perfect vector for infection, a protein capsid that just bonds to the cell receptor, and then it penetrates and injects its genetic material. And it's like a program, because a virus can't hurt you by itself. It can't reproduce by itself. It's not alive. Your enzymes have to read it and create what it tells you to create. If they don't do that, it can't hurt you. It's nanotechnology. See, a microbiology student would be like, well, our professor says that viruses come from the rainforest often because it has a similar temperature to a human's body temperature. Yeah, okay. Come on, people, it's technology, alright? There's no reason for a virus to exist in nature. Think about it. What are the odds of that? That you'd have the correct codons to be a viable fragment of DNA or RNA, and a delivery vector, protein capsid around it? Come on. And look at HIV. With AIDS, you get in your immune system, for your white blood cells anyway, you have a system. You have different types of white blood cells. Most of you don't care about this, but in case there's those physiology students out there that need to hear the technical stuff, because I won't be qualified to you unless I know what you know. Yes, I know what those are, the eosinophils, basophils, neutrophils, okay, and then you've got your monomorphs, and those are the T and Bs, and the monocytes, which you call a macrophage when it's in the body because it's mobile. The macrophage is kind of like the cop, alright? It's always going around your body sampling stuff, looking for anything that it would consider to be an antigen, or something that it sees as foreign to the body. So if it finds something like a bacteria that's foreign, that's infective, it will engulf it. That's why they call it a phagocytical cell. P-H-A-G-O. Phag means to engulf, to eat. Cyte means, well, cell. So it's a phagocyte. So it will engulf it and then display its material, the contents of the bacteria, on its cell wall. Then it takes a little trip into, say, a lymph node. There you have many white blood cells already there. In fact, you're born with, I guess, up to like 500,000 different types of combinations already there to handle infections. Like, you're already pre-programmed to fight off up to 500,000 different potential infecting agents, right? But it's very generic, so if something new comes into your body, what happens is this macrophage will go in there and say, hey, you know, look what I got. Of course, no, it's not speaking English, all right? I'm just being metaphorical. It goes in there and says, look, anybody here know what this is? Anybody, can you handle it? So eventually maybe this macrophage encounters a white blood cell that says, hey, wait, I kind of have something that can deal with that. That's pretty similar to how I'm made. Here, just give me a moment. Let me change a few things up. They call this genetic recombination. So it changes its genetic sequencing a little bit so that it can effectively go after the infection. Once it's done, and once it's changed itself to be correct, and so that it can handle it, it divides and puts clones of itself dormant. They call those memory cells, and that's your immunity, in case that pathogen comes back to the body again. So you don't have to go through this whole process. But when it's identified and says, okay, I'm the one to take care of it, then it will turn on a receptor on its cell wall, and all the other ones will turn their receptors off. And this is a receptor to a substance called interleukin-2. Inter means between, leukin means white blood cell. It's a hormone secreted by your helper cells. And what this hormone does is it causes rapid cell division. They divide fast. I mean, your lymph nodes will literally become packed wall to wall with white blood cells. This is why a doctor will feel your lymph nodes, right? If they're swollen, that means that your immune system's trying to fight something off. HIV goes after the helper cells, the one that secretes interleukin-2. So without that, you don't get the rapid cell division. Yeah, I'm sure that just happened to show up in the rainforest somewhere as a freak of nature. No, man. Viruses are nanotechnology. Viruses add genetic sequences. That's what many of your infections that you pass off as a cold here or the flu there, they're actually changing your DNA. Yes. But how do you resist a virus? What's a carrier? You hear about carriers. Well, this person's a carrier. They're not suffering from the symptoms, but they're a carrier. Well, if you're a carrier, that means that your white blood cells obviously didn't consume the virus. They didn't eradicate the body of the virus. Otherwise, what do you carry? Generally, because the virus is just too small. It's too small or intracellular or something. But why aren't you manifesting symptoms of it? If one person gets the warts virus and expresses warts once and then does not express warts again, and another person gets it and keeps expressing them, what's the difference? Well, the one that doesn't express it figured it out. Hey, this is doing all this stuff. Don't read that, basically. And then transmits that information throughout the entire body. Everybody, listen up. This genetic sequence, don't read it. It does this, 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 and this. Ignore it. And see, the thing about a virus, if you don't read it, if you don't follow its instructions, it can't hurt you. Period.